This is problem 9 from chapter 33. So the question is, what's the apparent brightness of the sun as seen from Earth, Jupiter, or seen on Jupiter? Jupiter's 5.2 times farther from the sun than the Earth. And so I think we're supposed to divide by 5.2 squared, but let's just look at it. So in problem 8, they give us the solar constant as 1.3 times 10 to the third watts per square meter. And I think we calculate it last time at about that, like 1,300 watts per square meter striking the Earth's atmosphere, right? And so the apparent brightness, absolute luminosity of the sun. What is the apparent brightness of the sun as seen from Jupiter, right? And remember that the brightness is the luminosity divided by 4 pi d squared, right? Okay, so what we're saying here is that 1,300 is the luminosity of the sun divided by 4 pi d squared, right? And this is for the Earth, right? And this is 1 astronomical unit, right, in meters, times some constant, right? Right, some conversion factor, yeah? What?
You were laughing that I was eating pickles.
Pickles.
And now everything here smells like pickles.
Pickles are good. You need to eat a pickle, you got to eat pickles, you know? Okay, so then the question is, and Jupiter, right? Jupiter is going to have some x watts per square meter, isn't that right? Okay, and that's going to equal the same sun divided by 4 pi, and then it's going to be 5.2 AUs times the same K, right? And the K is just whatever converts AUs to meters, right? So that's going to be, I think, what is it, 1.5 times 10 to the 11th meters or something like that? Is that right? But it doesn't really matter because we don't need to know that because can't we just do something with this? Yeah? So I've set up the two equations. Here's the Earth, right? Don't we know that L is L? It's the same sun, right? And we know that this is 5.2, so we can just divide these guys, right? So then you get 1,300 over x, right, equals, and then ultimately, by the time you've done turning all this stuff over, I think you end up with 5.2 squared over 1 squared. Because aren't the L's and the 4 pi's are all going to cancel out, aren't they? I don't think so. Because it's 1 over 1 over, right? So it's 1 over 1 squared plus over 1 over 5.2 squared. So I think then that, yeah. I think, and now we can just cross multiply. Ultimately, though, the answer was, I'm showing you why it is, but the answer is just you divide by 5.2 squared, right? I believe. Does that get the right answer? Because I'm willing to back off of that statement if it's not the right answer. Is the answer 1,300 divided by 5.2 squared?
It's like 48.
Yeah, 48.0.1 watts per square meter. So X is 48.1. That's a cold sun, huh? On our coldest, darkest days, it's like 200 watts per square meter or so, you know. Yeah. That's the solar constant. That's what it is hitting the Earth's surface or the atmosphere, the upper atmosphere. Not quite that much gets down to the surface. So it's like 1,000 watts per square meter. When I was like in 7th grade, I read an encyclopedia entry and misunderstood it because it talked about the watts of power leaving every square meter of the sun. Can you imagine what that is? Yeah, kind of like a lot, like a bajillion. And so I was amazed by this, right? They were talking about not the square watts per square meter hitting the Earth, but leaving every square meter of solar surface, right? You know, so I read this thing and it was like 5 million billion watts or whatever it was. And I'm like, holy cow! So I quickly went out and built a solar collector. It was just a box with like Saran wrap over it, and this thing was going to like power the city of Cedar Rapids and New York and Los Angeles or something because it, right? Yeah. It just got warm. That's all it did. Got warm. Didn't. Yeah. I know. All these things, right? I could have invented a perpetual motion machine and I didn't. Sad.